Welcome back to our video series on anaerobic digestion. Today we'll be discussing the temperature ranges commonly used in anaerobic digestion. Temperature is a key operational parameter. Deviation from ideal temperature ranges can lead to severe operational problems in reactor performance, as methanogens are highly susceptible to temperature changes. As shown in the chart here, methanogens can be classified into three broad categories based on their ideal growth temperatures: psychrophilic methanogens, mesophilic methanogens, and thermophilic methanogens. The majority of engineered anaerobic reactors are constructed for mesophilic or thermophilic temperature ranges due to their superior methanogenic activities. Mesophilic microbes work effectively within their optimal temperature range, as illustrated in the chart assembled by Danish researchers here, depicting methanogenic activity on the y-axis and temperature on the x-axis. It is noteworthy that the y-axis is a logarithmic axis in this diagram. As the temperatures drop below 33 degrees Celsius, the methanogenic activity declines logarithmically, and at 25 degrees Celsius, it is only at half the value compared to 35 degrees Celsius. The ideal activity range for methanogenic activity is between 33 to 38 degrees Celsius. On the other hand, if the temperatures exceed beyond 45 degrees Celsius, the reactor may experience a major upset, as seen in this figure. This phenomenon occurs because microbes have extracellular, intracellular, and membrane-bound enzymes, and their cell walls are made of lipoproteins and other biomolecules. Microbial survival and activity depend on stability and activity of these microscopic biomolecules. These biomolecules have 3D structures that are essential for their activities. These enzymes and proteins can denature when heated beyond their optimal temperatures. Such a change in the protein structure is called coagulation. Once coagulated, these enzymes may not fold back to their original three-dimensional structure upon cooling. This phenomenon can be observed when an egg is boiled and cooled. The originally translucent egg internals don't return to their original state. Coagulation of non-thermostable biomolecules often leads to their irreversible inactivation and hence death of methanogenic cultures. Although the function of such reactors can be eventually restored by gradually adapting these cultures to higher temperatures, this adoption is often non-practical for full-scale reactors. Often such reactors are reseeded with new methanogenic cultures to resume their function. In a nutshell, if a reactor temperature of a mesophilic reactor exceeds 45 degrees Celsius, there may be a severe irreversible loss of reactor activity. On the other hand, when the temperatures decline below the optimal levels, these enzymes function suboptimally at a lower kinetic rate, resulting in sharp decline in microbial activity. Researchers have modeled this decline using Arrhenius equation and its modified forms. The graph compiled by Danish researchers is shown here. This chart summarizes the work of several researchers, and it shows the temperature dependence of the methanogenic activities of mesophilic methanogens. If the temperature declines from the optimal operating temperature to a certain degree, a complete recovery is still possible, as long as the feed to the reactor is managed by the decline in the activity as shown on the y-axis. This chart also indicates that below 17 to 20 degrees Celsius, very little methanogenic activity is practically feasible, and hence the majority of engineered mesophilic anaerobic reactors operate in the 35 to 38 degrees Celsius range. Another class of methanogenic reactors is increasingly becoming more common in the waste-to-energy industry. These reactors operate at thermophilic temperatures and often achieve higher organic loading rates due to their ability to carry out hydrolysis reactions at faster rate. Please note that the hydrolysis reaction is the rate-limiting step in digesting non-soluble particulate waste materials. These reactors employ methanogenic cultures with biomolecules that are thermostable at higher temperatures, operating between 55 to 65 degrees Celsius. Another advantage associated with thermophilic reactors is that the carbon dioxide solubility declines with increasing temperatures, resulting in less carbonic acid formation in the reactor fluid. This can decrease the alkalinity demand in thermophilic anaerobic reactors treating carbohydrates. However, an increase in temperature also carries potential risks that operators and design engineers must be aware of. Higher temperatures impact the growth of methanogens, and some studies have shown that thermophilic methanogens may have 50% biomass yield compared to mesophilic methanogens. Moreover, only a few methanogenic species can function at higher temperatures, reducing the methanogenic diversity in these reactors. Lower methanogenic yield and lower diversity increases the chances of reactor upsets. Moreover, the adoption of thermophilic methanogenic cultures to a variety of substrates poses a significant challenge due to their slow growth rate. Finally, a higher fraction of the ammonia nitrogen is in the unprotonated toxic form at thermophilic temperatures. The concentration of this toxic form of ammonia increases almost 3 times at thermophilic temperatures compared to mesophilic temperatures, further increasing the chances of reactor upsets. This concludes this video lecture. I hope this presentation provided you with insights into why temperature is such a crucial parameter for anaerobic digester operation. If you have any further questions on this subject, please feel free to contact our anaerobic digestion expert at the contact details given below. Thank you so much for your attention, and I look forward to seeing you in the next lecture of this video series. Bye-bye.